Probability. So today we're going to start on probability. We'll be doing some more stuff next week, but we're going to look at some terms used in the subject of probability, what the laws of probability are, do some work problems on that, take a look at permutations and combinations, and binomial expansion using Pascal's triangle. Alright, so that's the topics for this morning. First of all, probability. Probability of something happening is the likelihood that it will happen. Values of probability will always lie between the values 0 and 1, where 0 represents an absolute impossibility and 1 represents an absolute certainty, and then you've got all the other probabilities between those two. So for example, the probability that length of wire has 0 resistance at 100 degrees C is an absolute impossibility, therefore it has a probability of 0. But you get that fair six-sided dice would start with a 3 upwards. Well, there's 6 numbers on a dice, so the probability of getting a 3 is 1/6. That a fair coin will land with a head upwards. Well, there's one head and one tail, therefore the probability of getting a head is a half, or 0.5. That a length of copper wire has some resistance at 100 degrees C is an absolute certainty, and therefore is a probability of 1. Okay, so what we have is P is the probability that something will happen, Q is the probability that the same event will not happen, and therefore P plus Q must always equal 1 in any probability problem. So all the probabilities that you've got of all the different events that could happen should add up to 1. So if you think about the dice, there's 6 different numbers on the dice, all got a probability of a 6, and therefore if you add all the 6 together, you end up with 1 probability overall. That's going to come up with some number or other. Okay? Everybody happy with that so far? Dissenting voices, I'll move on. Right, expectation, E, of an event happening is defined in general terms as the product of the probability P of an event happening and the attempts made at that event, N. So, since the probability of taking a 3 upwards when rolling a fair dice is 6, as 1/6, the expectation of getting a 3 upwards within 4 throws is a 6 times 4, 2/3. Yep. So, dependent event. Dependent event is one where the probability of an event happening affects the probability of another event happening. For example, we take 5 transistors at random from a batch of 100 for test purposes, and the probability of a transistor being faulty, P1, is determined. If at some time later we take a further 5 transistors from the remaining 95 that are in the box, the probability of faulty transistor is again calculated P2. The probability P2 will differ from P1 since the batch size has changed from 100 to 95. So that means that probability P2 is dependent on the probability P1. For this reason, the second random selection is said to be without replacement. So you're taking a second sample without replacing what you took in the first place. Then we have independent event. This is one where the probability of an event happening does not affect the probability of another event. For example, our 5 transistors again, if we take 5 out and we determine that the probability of them being faulty is P1, but if at some time later we put back the 5 transistors, we put randomly back 5 transistors and bring the batch size back up to 100, and then calculate P2, the probability of P2 will equal P1. Since the 5 transistors were replaced between random draws, the second selection is said to be with the replacement, and they are independent events. Okay, everyone happy with that? So, conditional probability is concerned with the probability of, say, event B occurring given that event A has already taken place. If A and B are independent events, then the fact that event A has already happened will not affect the probability of event B. If A and B are dependent events, then the fact that event A has happened will affect the probability of event B. Okay? So, conditional probability. Everybody still happy with that so far, these terms? And you might need to look back at these when we start working on some problems. So, laws of probability. First of all, the addition law. The addition law of probability is recognised by the word or during probabilities. So if we talk about the dice again, we could talk about what's the probability of getting a 1 or a 3 in a fair dice. When you hear the word or, and the probability of event A is probability A, and the probability of event B is PB, the probability of event A or B happening is given by the two probabilities added together. So the word or in a probability problem means we add the two probabilities or more together. Provided the two events A and B are mutually exclusive, they cannot both happen. So you can't get 1 and 3 on a dice at the same time, can you? Similarly, if there are 3 or more events, then the probability of one of them happening is all the probabilities of those 3 or more events added together. Okay, remembering that if we add all the possible probabilities together, that would add up to 1. So if we said what's the probability of getting a number from 1 to 6 on a dice, that's an absolute certainty because we're going to get one of the numbers or other. Okay, again, all okay with that? So the additional law of probability is for the term or. Multiplication law of probability. Multiplication law of probability is recognised by the word and joining the probabilities. If the probability of event A is PA, probability of event B is PB, then the probability of event A and event B happening is given by PA times PB. Similarly, if there are 3 or more events, then you multiply all the probabilities up to get the probability of all those events happening. Now, so when you see and probability of in 2 rolls getting a 1 and a 3 on a dice, and you calculate the probabilities of each of them and multiply them together. Alright, let's have a look at some problems. Determine the probabilities of selecting at random A, a man, and B, a woman, from a crowd containing 20 men and 33 women. How do we work out that probability? A. Yep. So what it is it's the number of men that we have in our sample divided by the number in crowd. Therefore, probability of a man, PM, equals 20 over 53 which is, gentlemen, therefore, yep, 0.378. Yep. And B, the probability of a woman is put it down as total this time. P women equals, what's that, 33 over 55, 53 equals we got
0.623.
yeah, and the check is that they're both correct. Add those two together, what do we get? It's a little bit out because you've rounded them, but yeah, no, 1. Yep. Did I start that today? Yeah. Okay. Right. Second problem. How to go at that? Find the expectation of obtaining a 4 upwards with 3 throws of a fair dice. First of all, what's the probability P?
1 times 6.
1 times 6.
1 over 6 times 1.
Yeah. The probability P of getting a 3 is a 6. Yeah. N is 3 attempts. Guys, lesson please, not other things. Right. Expectation therefore is N times the probability half. Yep. Or 3/6 half. Calculate the probabilities of selecting at random the winning horse in a race with 10 horses are running. The winning horses in both the first and second races, if there are 10 horses in each race. Fairly easy problems these, aren't they?
With the one with the one, it's like the does 3 times. We're going to get 4 half the time.
The probability of getting a 4, that should be, sorry. Probability of getting a 4
Yeah, right.
is 1/6.
3 times. Yeah. I'm not going to get 4 much.
Now,
You get a 1/6 chance.
the expectation that you'll get, it's an expectation, not a probability. I can I kind of see what you're saying, but it's an expectation that you would, in 3 attempts, get a 4 as a half. Because you're having 3 goes at it. So you must have 3 times the 6. The chance of getting a 4 on one throw is a 6. Yeah?
Oh, I read it.
So your expectation of doing that, getting a 4 in 3 throws, has to be 3 times a 6.
Oh,
Yeah, it's not the probability of getting
What I meant is get a 4 3 times.
No, it's not probability. It's not getting it 3 times, it's getting it once in 3 goes. Yeah? So you must have 3 times the chance of getting a 4 if you shake the dice 3 times, must you?
Right.
Right? So the probability of getting a winning horse in a race with 10 horses, winning horse in both the first and the second race if there are 10 horses in each race. Yeah, we're using the multiplication law. Because we've got and in there, 2 events, and they're anded together, so therefore probability is equal to a 10th times a 10th, which is 100th. Yeah. Not very good odds, is it? Picking your horses at random. Right. Problem 4 says the probability of a component failing in 1 year due to excessive temperature is 1/20th. Due to excessive vibration is 1/25th, and due to excessive humidity is a 50th. Determine the probabilities that during a 1 year period a component I fails due to excessive temperature and vibration, B fails due to excessive vibration or excessive humidity, and C will not fail at all because of both excessive temperature and excessive humidity. Take 5 minutes, have a go at that question. Right, think carefully about the last one, C. Right, gents, A, probability of failure due to heat or temperature and vibration. What's that equal to? Yes, that's the probability of temperature times the probability of vibration. So that's 1/20 times 1/25, because that's and. So it's the multiplication law, because we got and in there, which is 1/500 or 0.002 if you prefer in decimals. Yeah. In a question that wouldn't really matter. When you get the ones like the dice with a 6, you're definitely better. If you're going to use calculate on, you're certainly better to keep the fraction, because then you're not rounding it at all, and at the end they will all add up to exactly 1 if you got them right. Okay, so I would recommend staying with the fraction, certainly if you're going to calculate on from that position. So if you're going to use that value, a 500th is exactly 0.002, but where you've got 6 and 3 thirds and things, keep the fractions, I would. Okay. B, probability of fail due to vibration or humidity is equal to so that's probability of vibration plus probability of humidity, which is 1 over vibration is 25 plus humidity is 1 over 50. Yeah. What do we have to add two fractions together?
Put it into your calculator.
Yeah, or make the denominators common, so that's 2/50ths plus 1/50th equals 3/50ths. Agreed?
Yeah.
Which is 0.06. Alright. Right, what about this last one? How do we do that?
1 minus 1 over 20 times 1 over 50.
Tell me where that comes from.
Rather than it being failed due to, is will not fail.
Yep.
So if we do it as if it were failed due to, and then just
Well spotted. C. So, probability will fail due to, what was it? Temperature and humidity equals temperature's 1/20th and as times humidity's a 50th equals, yeah, and you've done that. What was the answer to that?
100,000.
Yeah.
Yeah, that's 1.
Hang on. It's not. I've gone wrong here. Let's have a look at this answer. We got these two probabilities right here. Because that ain't the answer he's got in here.
So you add it.
40 million. No, he's done it. He took the inverse probabilities. What's your answer? you see why your answer's wrong? Never can I, but according to him it is.
What is it?
Right, let me show you what he's done. I'll leave that on the board. Right, what he's done is, if the probability of fail due to temperature is 1 over 20, then the probability of it not failing, and that's what you use for that, not failing due to temperature, must be 19 out of 20, because those two have got to add up to 1, remember. Yeah? And the probability of it not happening due to vibration is 24 over 25. Yeah? And the probability of it not happening due to humidity is 49 out of 50. Yeah. So what we're looking for part C is the probability of not temperature and the probability of not getting humidity. That's 19 over 20 times 24, 49 over 50. Give me the answer to that.
Over 1,000.
931 over 1,000. In your calculator, add those two fractions together. What do you get? Just put them in as fractions and add them together.
193 over 100.
Yeah. I can see what you're trying to do. Take the probability of happening away from the overall probability, but you're taking two different events. So you have to do it that way. You have to find the inverse probabilities, or sorry, the probability of it not happening, and then add those two together. Alright? Separately. Because what you're trying to do is you're taking the overall probability and then looking for the inverse of that. What you're doing with the method you used is you're taking the probability of T and you're adding that with the probability of H, and then you're taking the inverse of the whole thing. And that's not the same. I don't want to go into a load of stuff about Boolean logic and why that and that aren't the same, but they're not. Okay? So, where you've got inverses, where you're looking for it not happening, look for the other half of individual, and then add them or multiply them together. Right, so just watch out for that. Right, last problem for you to have a go at. Batch of 100 capacitors contains 73 which are within the required tolerance value, 17 below the required tolerance value. The remainder are above the required tolerance values. Determine the probabilities that when randomly selecting a capacitor and then a second capacitor, A, both are within the required tolerance values when selecting with replacement, and B, the first one drawn is below and the second one drawn is above the required tolerance value when the selection is without replacement. Yep, let's have a go at that one. Yeah, because we're replacing, still the batch size is the same, and so it's just the two. So if the probability of picking one that is within the required tolerance is the tolerance of getting one go multiplied by the same tolerance. The answer to that is 5329 over 1,000.
How do you know?
You don't. You're placing it with another random transistor. Yeah. Well. Yeah. That's what the assumption you're making, is it? That's why I'm not overly keen on the question, to be honest, because I think normally you'd be talking about taking a batch of more than just one anyway, and you'd normally not take a second sample or do it without replacement, I think. A bit contrived, really, the question, because that's not in my opinion. 0.5329 as the four significant figures. Right, what about B?
We've already did this one.
Sorry?
This was,
First one drawn below. Probability of first one being drawn below.
17 over 100.
Yep. And what's the probability of the second one being drawn? Is above on the second draw. So what's the probability of above?
99.
This is where I don't like the question, because what you're doing is assuming, if you say 9 over 99, you're assuming the first one you took was above, and that could have been above, below, or in the middle. So the way he's done it is,
Oh, it says the first one drawn below.
Where does it say that?
Oh, yeah.
No, the probability that the first one drawn is below. Determine the probabilities that when randomly selecting a capacitor and then a second capacitor, the first one is drawn below and the second one's drawn. I see how you're interpreting the question, Dom, but it's not meant to be interpreted that way. I agree with you. On reflection, looking at the question, I wouldn't have put it in there. Right? But what he's done is, he said that there are 100 minus 10 minus 73 chances of above. Having took one away, and if you said, well, we'll take one away, which one are you going to take? Because you don't know what the first one was. Yeah. Yeah. So it's done. That is 10, isn't it? No, 17. Is it not? Difference, 17, sorry. 100 minus 10 is 90, minus 73 is 17. Yeah? Where's he got 10 from then? That's the probability of below, 17 out of 100. What's the probability of above?
Okay, go on.
Probability of returning a capacitor below the required tolerance value on the first draw is 17 out of 100. There are now only 99 capacitors left in the batch. Since the first capacitor is not replaced, the probability of drawing a capacitor above the required tolerance value in the second draw is 10 out of 99. Yeah. Thus, the probability of both those happening is 17 over 100 times 10 over 99, which equals 170 over 990, which is 0.0172. Yep. So that one sample taken in the first place, you don't know which whether it come out of the 17, the 10, or the 73. Does that pass it? Yeah. There we go. I think I might take that question out for next year, because it's not a very good one, is it? It's not very well written. No. Right. Permutations and combinations. Permutations. If we have n different objects available, can be arranged in different orders of selection. Each different order arrangement is called a permutation. For example, if we take the letters X, Y, and Z, we can have X, Y, Z, X, Z, Y, Y, X, Z, and so on. And the order, a different order, is a different permutation. So order matters. There's a mathematical way of expressing that as the 3p3 in that format is equal to 6. So there's 6 permutations. We raise 3 denotes the number of items from which the arrangements are made. So there's 3 items in X, Y, and Z, and the lowered 3 represents the number of items in each arrangement. No, because if you what you're saying is if you go have I got it on the page or not? If you had 3P2, and how many different combinations of 2 letters are there in 3 letters? How many permutations of 2 are there in 3? Right, so they aren't the same thing. Please, this 3, yeah, that's the number of items from which the arrangements are made. So how many items are there? Hey, we've got X, Y, and Z. And the other 3 is how many of those items we put in each permutation. Doesn't have to be 3, does it? So if we go 3P2, we get XY, we can have YX. Yeah, we can have YZ, ZY, and we can have XZ and ZX. And this just happens, there's still 6 of them. They're the same thing. Yeah. We got 3 in the set, X, Y, and Z, but in each permutation we're only including 2 of them. Yeah? Whereas here, we got 3 of each, and we're including all 3. Happy with that, or not? Sorry, Toby?
That has nothing to do with taking
No, it equals 6. That means how many permutations of 3 letters are there in a set of 3 letters? And there are 6. 1, 2, 3, 4, 5, 6. Looking at the next page, if we take the letters, if we take the same 3 letters, X, Y, Z, 2 at a time, the permutations can be found, and I'll just root these out. X, Y, X, XZ, ZX, YZ, ZY. So, it just so happens in this case that 3P2 is also equal to 6 because there's 6 permutations. If we took 1 letter from 3, it'd still only be 6, wouldn't there? Yes, X, Y, and Z, sorry, it would only be 3, wouldn't there? 3 permutations of 1 from 3. In general, the number of permutations can be found using that formula. NPR is N exclamation mark of N minus R in brackets exclamation mark. The exclamation mark means factorial. So it means all the numbers up to that number multiplied together. So 5 factorial is 1 times 2 times 3 times 4 times 5. You have a factorial button on your calculator. That's on one of the shift functions. So from above, if we want the number of permutations in 3P2, we do 3 factorial on top of a fraction, 3 minus 1, which is 2 factorial on the bottom, comes out at 6. Three factorial is 6 And hang on, I can see why you're getting the wrong answer. R is 2. That's why. Misprint. Because N is the number of different items, so that's 3. And R is the number of items in each permutation, that should be 2. So now it's 6 over 1, which is 6. So again, for the misprint. Alright? Yeah. Right, combinations. If selections of 3 letters X, Y and Z are made without regard to either of the letters in each group, i.e. XY is now the same as YX, for example, then this is called a combination. The number of combinations is denoted by NCR, where N is the number of different items and R is the number of items for each combination. So, in general, NCR is N exclamation mark over R exclamation mark times brackets N minus R close brackets exclamation mark. So it's like the formula for permutations with the R exclamation mark added on the bottom line. So for example, the number of combinations of 2 letters out of 3 letters is 3. There's 3 pairs and 3 selections. Alright, those of you that are horse racing inclined will know that there's 3 pairs in a round robin. Never heard of that.
I'm not very well educated there.
You don't do your horse racing then? You heard of pairs and doubles and everything when you bet, have you, or do you not bet at all? No. Okay. I'm not trying to encourage you to bet, by the way. So, just by example, yeah, the old lottery before it went Euro Millions, you picked 6 numbers from 45. Was it 49? 49. How many combinations is that? How many different ways can you pick 6 numbers from 49 numbers? That's going to be 49 factorial, which is a lot, over 6 factorial, 39 minus 6 factorial. I wanted to do Euro Millions, but I didn't realise that's like 2 different, you could select 2 different sets of numbers, which is a bit more complex to do.
Let's do it.
What do you get?
Does it get explanation mark?
That's factorial. So I mean, all that top line, I mean, we multiply all the numbers up to 49 by each other. You got on the calculator there, look.
Oh, right, okay.
Yeah, so you can do... Anyone got me an answer yet? I think that's 14 million and something from memory.
Where do you get the 6 from?
6 is how many the 6 is how many numbers you pick, and the 49 is how many you pick them from. So the old national lottery used to go from 1 to 49. Yeah, and you pick 6 numbers on your selections. So how many different ways, what we're working out is how many different ways, not order doesn't matter for picking 6 from 49. And I think that's 14 million somewhere, isn't it? Is that 13 million something? 13,983,816 different combinations. So if you'd done a ticket with all them on, you'd be guaranteed to win. The trouble is, you'd be paying £1 for each go, and you might win something like that. That's £2 now, but the old lottery when it first came out was £1. And no, well, yeah, when you get rollovers, but yeah. But then you're talking about paying it every time, aren't you? So Euro Millions must be lots more combinations than that. Somehow, I'm not even going to try to do it. So, problem 1. Calculate the number of permutations there are of 5 distinct objects taken 2 at a time and 4 distinct objects taken 2 at a time. So A, we're looking for permutations from 5 objects taken 2 at a time, and B, permutation for 4 objects taken 2 at a time. In fact, have a go at all 3 of the problems that are there, and then we'll confirm the answers. Right guys, first 2, you should have permutations of 2 from 5 is 20, and permutations of 2 from 4 is 12. And then the second problem, combinations, different formula, remember. You should have combinations of 2 from 5 as 10, and combinations of 2 from 4 is 6. And the last problem, look for combinations of 4 from 24. 20 and 12.
That's one.
10 and 6. So here we're looking at 24 factorial over 4 factorial and I got 10626, 10,626 combinations of 4 from 24. Yeah, you should always remember that combinations, order doesn't matter, permutations, order does matter. Okay? Right, last little bit for today, binomial series. Remembering that here, permutation-wise, we're talking about the permutation of an event happening P, and the permutation of it not happening as Q. So overall, they are P plus Q. And what we're doing here is something that leads into the binomial distribution that we're going to look at next week. So a binomial expression is the one that contains 2 terms connected by a plus or a minus sign. Examples include P plus Q that we looked at this morning, A plus X squared, 2X plus Y cubed. Come in, Adrian. Come in. Oh, you want me to? Right. Is it that bad, Logan? Right. So if we were to expand expressions like A plus X to the n for integer values of n from 0 to 6, we get results like this. We're not going to do that because that's a bit of a mind-numbingly awful thing to have to do, is multiply all them out by hand, okay? But what you can notice from this, from the results here are that I decreases in power from left to right. So if we look at from left to right in any expression, so let's take this one, a to the 4, a to the 3, a to the 2, a to the 1. We could even argue that there's a to the 0 in front of the x to the power 4 on the end, because a to the 0, gentlemen, equals
Absolutely 1.
absolutely 1. You nearly said 0, didn't you?
Yeah, no.
Yeah, so you can note that x increases in power from left to right. So looking at the same one, we could argue that we've got x to the 0 in with that a to the 4 there, x to the 1 in here, 2, 3, 4. So that's the other fact about that. The coefficients in each term, so the coefficients are the numbers in front of the terms, symmetrical around the middle coefficient when n is even, and symmetrical around the middle two coefficients when n is odd. So if we look here, symmetrical around the middle two, and here symmetrical, so we've got 4 and 4, 1 and 1, and so on. The coefficients are shown separately in this table, okay? It's known as Pascal's triangle. Alright? So, what you can note about that is, the number, if we look at these triangles, the number below, in between, is those two numbers above, added together in every case. 3 and 1, 4 underneath. 10 and 5, 15 underneath. So we can always create the next row out of the previous row. By adding.
What is fusion?
Sorry? It can be used to expand these binomials raised to powers up to about powers of 10. Beyond that it gets a bit unwieldy. There's a formula method that we're going to look at next week. Okay. Binomial is an expression like this. Two terms added together. Alright? But remember what in terms of what we were looking at, what looked at first thing this morning, Toby, was that if you've got something that's P is the chance of something happening, and Q is the chance of that same thing not happening. So you've got a binomial choice, one thing or the other. You can't get both. So there are the probabilities involving that, and then throwing that head or tail 5 times, and the probability of getting 5 heads in a row or getting 4 heads and 1 tail as a binomial probability. Because every time you try it, there's only two different and exclusive things that can happen, one or the other. Yeah? It'll become clearer when we actually use it, I agree. But at this moment in time, just want to look at Pascal's triangle as one way of expanding that a plus x in brackets all squared. Right? That one's fairly easy because, let's have a look at them just to show you that it is helpful. If we look at expanding a plus x squared, how do we do that? What does that mean? What does that mean we do? Ax squared.
Square the sum of A and X.
We have to do this, don't we? A plus x, it means a plus x times a plus x. Yeah? The answer to that is, what do we have to do? A squared, so you have to do a times a is a squared. A times x times a, and x times times x squared. Yeah, and if we bring the two ix's together, ix squared plus 2ix plus x squared, we have one of the lines, do we not, in that table? The ax plus squared line. 1, 2, 1 are the coefficients. Yeah? The coefficients are 1, 2 and 1. Coefficient is 1, 2, 1. Yeah? Now, how do we get a plus x cubed? Yeah, and we've already got a plus x squared there, so if we use the result of that, a squared plus 2ax plus x squared, put it in brackets, and we've got to multiply that by x plus a. Put them in the right order, Michael. How do we do that? A squared times a is a cubed. A squared times x is a squared x. 2ax times a is 2ax times x is x squared times a is and x squared times x is what we got in terms of like terms here. A squared x and 2a squared x is 3a squared x. 2ax squared and ax squared is 3ax squared, and then we've got x cubed on the end. And the coefficients are 1, 3, 3 and 1. Are they not? Is that not the next line in that Pascal's triangle? Yeah? Yeah, because you don't know why you're going to need to do a binomial expansion yet.
Yeah.
So I'm teaching you a skill at the moment that you're going to need to do a certain type of problem next week and maybe the first week back after Christmas. Yeah? So you have to kind of take a leap of faith at the moment that you need to know how to do this for a reason. Yeah? And if I asked you to do to the power of 6, would you want to do that by hand? Would you want to find the coefficients by Pascal's triangle? Even if I said 7 or 8, you could expand those down and find the coefficients, couldn't you? If I said do 25, you probably wouldn't want to. But if I did to the power of 7, 8, 9 maybe, then you'd be happy to do that via Pascal's triangle. Yeah? You got next week, and then that's off for Christmas. Well, I won't be here. Alright? So, Pascal's triangle can be used there. So, So, if we want to solve, for example, the next line in that column, we can use Pascal's triangle to do a plus x to the power 7, because we can take the previous line, we know it's 1 on the end because there's always 1 on the end, and then we add the 1 and 6 together to make 7, the 6 and the 15 together to make 21, the 15 and the 20 make 35, and so on. And in that line then we've got the coefficients. We know that the index of A decreases as we go from left to right. We know that the index of X increases as we go from left to right. So we just take the coefficients. A to the 7, 1. There's this coefficient of A to the 6x, coefficient of A to the 5x squared, and so on as you go through. So you can pick the coefficients out and do that binomial expansion. Yeah? So, problem. Determine using Pascal's triangle method the expansion of 2p minus 3q to the power 5. I think what we'll do, as I've had to go out and speak with Adrian and Omar, is we'll pick up on that one next time. Alright?
Thank you.